Have you all filled the form? Yeah? Can I have it? So I'll start by giving you guys a pretty difficult question that I had in my last year's assignment. I don't think you guys did it, and if you did, just let me know, and we'll skip over it. But it's regarding sequences, and as you saw, like last year's final has a lot of sequences in series, despite you assuming that he's not going to get a lot of stuff on the midterm, so it's important to still review this stuff. So our first question will be, let AN be a sequence such that all epsilon greater than 0, there exists an epsilon greater than 0, such that for all n greater than or equals to n epsilon, this is true. Did you guys do this in lecture? A2n minus an is less than epsilon. Okay. So the question is this sequence Cauchy? I might even be recalling the definitions because you're only 2 days away from the final, so you should be familiar with those definitions. And you have all the tools to solve this problem. It's not the easiest, to think of why or why not it's true. So I'll give you guys some time. But is the question clear to everybody? Yeah? Okay. The converse is clearly true, right? If this is Cauchy, then that's obviously true, right? Because then for all m n greater than n, you just take n to be 2n, right? Is this true? Let's first answer the question, is this sequence Cauchy first? And then if it is, then we'll then take some time to prove it, and if it's not, then we'll take some time to look for it. So do we think this is Cauchy or no? By a show of hands, is this Cauchy? You would think so, right? But it's not. Like the way I thought of it when I first saw it was like, if this is Cauchy, then they just would have given this as one of the characterizations of Cauchy, right? They would have been like, oh, this is equivalent to saying this, right? But they did it, so there's a reason why they did it. So what's the reason? What sequences could we make that fail the Cauchy condition but satisfy this? Think of some kind of invariance, something that when you multiply by 2, something doesn't change. There are many examples, but I'm using the one that I had when I did it. So.
Maybe we're just an equals n.
An equals n? No, No, because that doesn't even satisfy this, right?
Oh,
Yeah, because then the difference is always n, and n is not less than every epsilon, right? Yep. Negative 1 to the power of n. Let's see. 1 n. Sorry. Minus 1. 2n minus 1. The n. Right? Well, if this is odd. If this is odd, this is plus 1. So that means this is always even, right? So this is always 1, regardless. 1 plus 1 is 2, not less than. Right? Good idea. I know. So we put up the question on the board and we said this is not Cauchy. We're trying to find a counterexample. Okay? Give you guys like a cool, this is like the hardest eraser ever. Okay. Not necessarily. Again, so the converse is true. If it's Cauchy, it will satisfy this. Just pick m to be 2n, but we're looking for a counterexample with people. Okay.
It's just 1 over every.
1 over n. Well, 1 over n is also Cauchy, right? So we're looking for a sequence that is not Cauchy, but satisfies this. Because there are many that satisfy both, right? In fact, all Cauchy sequences satisfy both, right? So we know Cauchy if and only if convergent. So it's a good way to check. Just if your sequence converges, then it's not going to work. So look for a non-convergent sequence. It doesn't have to be non-Cauchy, right? Because non-convergent if and only if non-Cauchy, right? So non-convergent sequence, maybe a piecewise sequence defined so that when you multiply something by 2, something doesn't change. So, I want A of n. Okay. So we want some property here. So n has some property here. When n has some property, so let's say p of n, predicate, right? We have some property, okay? Such that when you multiply p of n by 2, you get the same value here, right? So that way you have a2n is equals to an for all n. This is what we want. We want the same thing here. So we have q of n, some property again. So we want two properties that are invariant upon multiplying by 2. Yeah.
maybe something like n if n is odd, 0
But then when you multiply the odd number by 2, it becomes even. So close. That's a good idea. Like he said, if n is odd, then you have some number like 0, and when n is even, you have some number like whatever. That's a good idea. We want to separate those two into two things. It's really close. I would say,
Define it based on the factorization of the things.
sorry?
Like doing was define your sequence based on the factorization of the things.
Almost, basically, kind of. So I was thinking of co-prime numbers to 2, because numbers that are co-prime to 2, when you multiply anything by 2 in that on those numbers, so say 3, right? So if n is equals to 0 mod 3, that means if n is divisible by 3, so n is a multiple of 3, 3, 6, 9, whatever, we have some number like 1, and then 0 other numbers. Why? Because if you multiply something that's not divisible by 3, if you multiply it by 2, it's still not divisible by 3, right? If something is divisible by 3 and you multiply it by 2, it's still divisible by 3, right? Yeah? So let's see why this works. Okay. Do we all know what this means? If not, I could rewrite it in like, if n over 3 is in the natural numbers. Okay. So case 1, when n over 3 is in the natural numbers. Okay, well this is pretty obvious because then you have n could be written as 3k for some k in n, right? Because it's a multiple of 3. Okay, and so then a(n) is equals to 0, a(2n), right, which is equals to a of 6k, which is still divisible by 3, is also equals to, 1, right? 1. So a(2n) minus a(n) is equals to 1 minus 1, which equals to 0, which is less than epsilon no matter what epsilon you pick. Right? And then, so is everyone good with this case? Yeah? So when it is a multiple of 3, and you multiply something by 2, it's still a multiple of 3. And so you're still 1. 1 minus 1 is 0. So I can erase it. Okay, case 2. So there are 2 more cases, case 2 and 3. First one is when n is equals to 3k plus 1. So 4, 7, so 10, right? Okay, in this case, 2n is equals to 6k plus 2, right? Which is not divisible by 3, right? Because this is divisible by 3, so this is gone, but this is not divisible by 3, right? And so then a(n) is equals to 0, a(2n) is equals to 0, and so a(2n) minus a(n) is equals to 0 minus 0 is equals to 0, which is less than epsilon for all that. Yeah? And then last case is just 3k plus 2. That's the only other case of numbers that we need to take care of. And that way all the integers or all the natural numbers are taken care of, right? Because you can write every natural number as 3k, 3k plus 1, 3k plus 2, right? And then if you cycle again 3k plus 3, that's the same thing as 3k, right? Case 3. So this will be 6k plus 4. And this is still not divisible by 3, right? So same exact thing. We get 0 again, and we're done. So this wasn't an easy question, I would say, but it was something that we did get last year's course. So maybe he just has a pool of questions that he picks from, and maybe this is one of them for your final, since it didn't come on the assignment. Okay. Last time I did the review seminar, we ended at sequences. So now we'll just start the series, and then we'll go to topology, functions. You guys only went up to continuity, right? Limits and continuity. Yeah, but in the final, about the final announcement, he said Kranz only up to 6.2 or something. So I don't think you're responsible for that. At least it doesn't seem like it. Okay, so question 2, part 1, give took 837, this should be like pretty doable. Think about it for a bit. So you want two series, they both diverge, but then when you multiply their sequences, and then you take the series of that multiplication of sequences, you get a convergent series. Yes? Yeah. So if you didn't hear him, he said 1 over n. It's a pretty standard question in analysis. So it's 1 over n equals infinity. Did you guys show this in class? Yeah. So 1 over n squared. Do we know this? Yeah. So when you multiply this by itself, you get something that does converge. Like a little side note, if you were to replace all n's with all even numbers or all odd numbers, it would still diverge. And if you were to replace n with all prime numbers, it would still diverge. Yeah, that's really interesting. Like prime numbers are very rare, but even if you replace with prime numbers, it still goes into so yeah. Okay, so that's part 1. Well, I'll leave it on the board actually. Okay, part 2. Okay, 2 sequences such find such a can we find such series? No. Who says no? If you're having trouble reading, just let me know. Also, front chairs are empty, so feel free to. Hands up for no. Cannot find. Hands up for yes, we can. Hands up for I don't know yet. Okay, let's wait like a minute. So do we have a way of relating this sequence with those two? That's what I would say you want to think about. You want to think about how can we relate these two series, to this series right here. And could we make it so that something less than infinity plus something less than infinity is infinity, so that we get a contradiction? Could we rewrite it in that way? To show that we can or cannot find such series? Yep, exactly. So we could do okay, and then we can just subtract. But then what is this going to be equals to? Right? Why can we do this? Because we can split those sums here. Right? If we have sum of a sequence plus another sequence, we could just split them into two series. So then this is the same thing as xn plus yn minus xn. Right? Could we all see the board, by the way? And so these cancel. And this is. But then why is this a contradiction? because this is less than infinity. This is less than infinity. But then this is equals to infinity, which doesn't make sense, right? You can't add two numbers, any real numbers, and get something infinite, right? Okay. Ready? Question 3. Absolutely. Then a squared converges absolutely. This one's an even easy. So I'll try the next question as well. Are we all good with this one? This one may be a bit more difficult. So yeah. Both true and false. True or false, right? Any ideas for this one? This side of the room? You guys think about this one? Do you guys have that one? Okay, so true? Yeah. Why? Exactly. So yeah. So this is true. Why? Because we know that an goes to 0, right? And when we square something that's less than 1, so there exists an n such that all n greater than or equals to n, an in absolute value is less than 1, right? When you square something, it's always positive, right? And when you square something that's less than 1, it becomes smaller, right? And so for all n greater than that same n, you have that an squared is less than or equals to an in absolute value, right? But this is positive, so taking the absolute value is the same thing as this is the same thing as this, right? And so it does converge absolutely by comparison test, right? Because this is absolutely convergent, and now this is absolutely convergent by CT. So by CT, this just got dim all of a sudden. The sun's gone. Okay. That's it. All right. There we go. Okay. Do we all see the board clearly? Yeah. Okay. Now what do we think about this one? False? Okay. Why? Jeremy said we could take AN, so take AN to be -1 shade to the n. Okay, and take Bn equals AN, right? The same thing. Yep, and then this converges by AS. Did we take AST in this class? Okay. No? Yeah? Yeah? No. Are we in the same class? Similar? Okay, well, do you guys have enough stuff to prove that this does converge as a series? Yeah, I mean, okay, yeah, okay. This does converge by, there's something that you could use, I'm sure, but typically you would use AST if you have it, because it's an alternating series. And yeah, Bn clearly does converge because you're taking something that's at most 1 over something that's going to infinity. And so Bn converges as a sequence. This is good. An converges, this is good. Okay, but then when we do Bn, or An times Bn, we get 1 over n, our favorite divergent series, right? And so very slanted infinity, but yeah. All right. Are we good on this one? Okay. Third part of this thing, last one, maybe also a bit difficult. If this converges conditionally, then n squared an converges. Do we know what conditional convergence means? Not covered in the course? Okay, well, so it means that this converges, but this does not. That's all you need to know. So, I mean, he could just define it in a question and then tell you to show something about it, right? Very. So this is what it means to conditionally converge. And I mean, it was covered in 837, so it's also a prerequisite. So. I'll give it to you, it's false, but try showing that it does diverge. So this necessarily diverges. Necessarily. Assuming that you have conditional convergence. So try to show it. The proof is like pretty short, but yeah. Maybe seeing that it was false was hard. I agree. first step. So suppose it does converge. What's like the most famous thing about convergence that we know of series? It's something with a limit. I didn't hear you, but I hope you said this. Well, the limit as n goes to infinity of this is equal to 0. Right? But what does that mean? What does it mean for this limit to go to 0? Well, we know that n squared is getting bigger and bigger, right? So here I'm approaching this by contradiction. I want to somehow find a contradiction. And the only assumption that we have is that it converges conditionally, right? So I want to contradict that convergence. Yep. And then exactly. So after this step, we know that there exists an n such that for all n greater than or equals to n, this is true. It's less than 1. Can we see, by the way? Perfectly clear? Okay, this is less than 1, right? But this also implies that for that same n, we have that the absolute value of an is less than 1 over n squared. But what does this tell us? What does this tell us? Right? So this is saying that by CT, the absolute value does converge. Right? Yeah? Comparison, we're comparing it with 1 over n squared, which does converge, and it's less than it, so it does converge. And we're taking the absolute value, so not only does it converge, but it converges absolutely. But our assumption was that it does not converge absolutely. And so this is a contradiction. I think that's the sign for contradiction, right? And so we're done. Because we showed that we have a contradiction, we contradicted the assumption, therefore, this series right here diverges. Are we all good with it, or do you have any questions? If you have any questions, now's the right time to ask because your exam's in 2 days. So. No? Alright, I'll erase this. You're gonna have to see that in the video. Alright. I don't think I was seeing the second board fully. Okay, perfect. Alright. I think it's about time we move to the next topic in the course. So you guys talked about topology in the real line, and proofs could be a bit tricky for this part of the course. I don't think you're responsible for connectedness though, as per the final thing, right? He said 5 to 5.1 to 5.4, and then 5.5 is connectedness. So 5.4 stops at the Cantor set, and then before that you have compactness, and then open sets, closed sets. In Krantz at least, that's what he was referring to. If you are, I know it was on your assignment, so that's why I was a bit weirded out, but yeah, just make sure you check what you're responsible for, because he posted the thing and I was also a bit shocked, so yeah. Alright. So what are we, Q4? 4, 5, 2 sets. Alright, so these are two sets, and the question is, the first question. What are the limit points of A and B? Alright, that's the first question. Second question. Are these sets open, closed? So where is this part? So what do we know about the limit point? What does a point being a limit point tell us? Yeah? Anyone definition of a limit point? No, we need to know this. Yeah? What can we also say about it? For every neighborhood around it? Yeah, for every neighborhood we have infinitely many points, right? Same thing essentially logically as a sequence converted, right? For any neighborhood around that point, you have infinitely many points. So it's very dense around it, therefore sequence converges to it. No matter how small your neighborhood gets, always infinitely many. Alright. So then we look at A. Let's look at A first. What kind of points do we have which always have infinitely many points around its neighborhoods? So it's super dense around those 2 or 3 or 4 or 5, 6, 7 points, whatever. However many limit points we have. Okay, so 1 is one of them. 1 is one of them. Okay. I'll answer over here. B. I'll denote it by L of A. Okay, just limit points of A. Okay, and then L of B. L of A we have 1. Okay, what's the other limit point of the set A? Hello. I don't think they heard you. So what's the other limit point? One of them is 1. One of them is 1. Why? Because, well, when we have an even n, right? So when n is even, we have like you see that? Points getting closer and closer to 1. Except it's actually from the right side. Right? So it'll be like, right? We have 1 plus 2 over 1,000, and then here 1 plus 2 over 1,002, right? So for all even numbers n, you keep getting closer and closer to 1 from the right. So that's one of them.
Would 3 be nothing?
With what?
3?
3? Why?
You could, so it would be, if n was odd, then you would get, the n was even, sorry. You would get that negative one to be a positive one.
Yeah, that's what it is here. Yeah.
It would be 1 plus 2 there, and then you could consider approaching to 1 plus 2 equals 3 with all odd, no, all even ends as neighborhoods.
It's not 1 plus 2, it's 1 plus 2 over n. Right?
But
So
that's what you
it's-
can construct a sequence of even ends that approaches to 3.
But the first term in our sequence is 3, or like the second one, let's say. It's close to 3, right? Actually, I don't even know if 3 is in this set at all.
It doesn't have to be for it to be
That's true, but what I'm trying to say is I think the furthest point away here is 2. The furthest point we can get is 2. Because when n is 2, this is 1 plus 1, which is that, and then for every other even n, it gets smaller. So let's say n is,
Oh, I see what you mean. It starts as.
yeah, and it keeps going to the left, right? Why? Because this is 2 over n.
So yeah, 2 would be that the left.
So this is basically going to 0, right? Yeah, exactly. So we go to 1, but what if it's odd now? What do we go to? Same logic, same exact logic.
It would be even, so it would be 0.
This is going to 0, okay? So
That would be good.
n is big, this is always going to 0, right? N is big, this is always going to 0. Even or odd, okay? Well, we said if it's even, this is going to go to 1, right? Well, if it's odd, what is it going to go to?
Negative 1.
-1, right? And so we have -1, and then we have numbers coming like this, because we have -1 plus some positive number, but super small positive number. So we're getting this close, right? So the other one is negative. All right. What about the limit points of B?
It would be just 0. 0, 1.
Okay, so we have one pretty
They're closing to the 0, 1.
close into the 0, 1. We all agree? Yeah.
Oh,
So a good way to check is if you conjecture that it is 0, 1, close interval, just pick any point you could think of in 0, 1, and then just keep taking small neighborhoods. Do we have infinitely many rationals around any point in 0, 1? Yeah, why? Because you guys showed in class that Q is dense in R, right? Don't you have infinitely many points between n? Yep, yep. Exactly, that's what he said. So he said the entire interval. Yeah. So like you're right as well. Yeah, it's good that you thought it was wrong and tried correcting it, because had he meant the other way, it would have been wrong. But he meant this, right? Yeah. So that every point here has infinitely many close rationals to it. So you can always pick some sequence of rationals that will approximate it as best as you can, right? And that's the same reason why we can't say that Q is open. Right? Why is the set of all rational numbers not open? Because you can converge to square root 2, right? If you're open, then you contain, right? So, yeah.
There's no neighborhood. I want any point in Q that's contained in Q.
Yeah. Is that why it's not closed? Oh yeah, that's why it's not closed, because it doesn't contain its limit points, which one of them is square root 2, right? Okay. And so next question is over here. Are these sets open or closed? So first, is A open? Sorry? Are they supposed to be what? For one sequence? Oh no, we can't have, well, this is a set of points, but the sequence is not convergent, right? So you could take two subsequences, one of them being the odd entries, one of them being the even entries, and then those two subsequences are convergent, right? Yeah.
So if we know 1 is in that set, because if we have 2 equals 1, n equals 1, so it would be negative, it would be 2 over 1, which is 2, minus 1. So 1 is in the set. But we have that, you can choose a neighborhood around 1, any neighborhood around 1 will be intersecting some rational point, and so it wouldn't be contained in this.
So are you saying that A is open or closed?
A is not open.
A is not open.
As for if it's closed, it contains this negative one.
So do we all agree that A is not open? A is not. In fact, intuitively, how could a set like this be open, right? It doesn't make sense. It's just a sequence of points, right? So A is not open. One argument you could say, just one argument is, we know that open sets in R are countable unions of intervals, right? Of open intervals. Did you guys show that? Right? But we cannot squeeze countably A. In fact, we cannot squeeze any AB to be a subset of it, right? Because it's just points, right? So it's going to be AA, but then that doesn't make sense. Okay. So next question is A closed? Well,
No, it doesn't contain -1.
pretty sure it does contain its limit points. Let's see. -1. Yeah. I mean, it's a countable set of points, right?
Oh yeah. Yes, practically squeeze.
And if you want to think about its complement too, for its complement, we could always squeeze in countably many open sets between the little. So you have one is here, then you have 2 is the first entry, and then let's just look at the even case. You have this. You could always squeeze in little open intervals to its complement, right? So that means its complement is open, right? And so that means it is closed, right? Okay, what about B? Sorry? Well, it definitely contains 1. That's what I was thinking of. I was thinking of, does it contain -1? Because if it's closed, then it contains its limit points, right? But I'm pretty sure it does contain its limit points. But I can't seem to find when -1 pops up.
Try to solve for -1.
Yeah, that's why I resorted to solving the complement, because like I'm almost certain the set is closed. It wouldn't make sense otherwise.
Second one is neither.
So yeah, maybe I'll address this in the break. We'll not fill it up, but I'm pretty sure this is closed. I'm like almost certain. Okay, so let's solve for B. We'll have a break, like literally in 2 minutes or something, and then I'll try to address it. Okay, so next question is B closed or open? Yep.
It's neither. For the same reason, it's neither. Because any point that's in Q, in the rationals, or it's not in the rationals at a neighborhood, intersects the other. And so it's going to not contain either its complement and itself is not going to be open.
Exactly. No. Same reason as why Q is neither. Same exact argument. You can construct a sequence of rational numbers in 0, 1 that converges to 1 over square root 2, right? And it also doesn't contain its limit points, you know. You also cannot write it as a countable union of open intervals. So therefore it's not open, but it doesn't contain its limit points, therefore it's not closed. Boom, you're done, right? So we'll take a 5-ish minute break because I still have some stuff to cover. And if I do finish early, I plan on like leaving the rest for any questions. Yeah, I do want to get to some questions here, so yeah, so 5 minutes. Yep, just let me end the thingy.